Right, so yesterday we finished topic A and move on to topic B, and then we just studied at this diagram only. Okay, so from this diagram, it provides evidence for us to provide the evidence that electrons are located on two different shells. Okay, so the first one, the outermost shell, and the second shell in the middle, and the shell that can only accompany two electrons. Okay, that closest to the nucleus. Okay, so today we're gonna focus on these 8 electrons. Okay, so now these 8 electrons, if we only consider that they locate on this shell, okay, so in principle, they should have the same distance to the nucleus, and then they should experience same shielding effect, and also we consider they should need the same amount of energy to remove them from this atom. However, when we look at this diagram, because this is successive ionization energy, that means when we remove this electron, okay, actually we're doing this. Okay, so that's for this electron. Okay, I'm pointing at this one. Okay, when we're removing the second electron, we remove this first one to get sodium plus, okay, 1 plus, and the second one we got 2 plus. And for the next one, okay, for this one, what we are doing is we're removing the third electron, so it should become Na3 plus. Okay, so here it's hard to say this increasing of energy needed to remove this electron, the third electron, whether it's due to they are located at a different distance on this shell or the increasing of charge. Okay, so here it got 1 plus. So when we remove a negatively charged electron, we require more energy to do that. But here it got 2 plus. Okay, suppose 2 plus should have a stronger attraction to this E minus electron. Okay, so hence to remove this electron, the third electron, we need to apply more energy to overcome that stronger attraction between 2 plus and this minus. Okay, so if we only look at the successive ionization energy, we can't tell what's causing this increasing in energy. Okay, so what we need to do is we're going to look at the first ionization energy. They're going to remove electrons from the atom on the same shell. Okay. So let's move on to page 4 of your notes. Okay, so here you can see this is a first ionization energy for the first 3 purest atoms. Okay, so from hydrogen, helium, okay, here, hydrogen, helium, and then period 2. So this is lithium from here, and then goes up to neon. And then the third period start from here, so start from sodium and then end with argon here. Okay, so here, if we focus on this area, this part, okay, so these 8 atoms, they are all from period 2. Okay, so for period 2 elements, this one, from lithium to neon, if we use the electron shell model you learned in grade 9, okay, so all the electrons, the first ionization energy means we're going to remove the electron from the outermost shell, okay, which is on the second electron shell. Okay, so we remove electron, so for example, lithium is going to be turned into lithium plus, okay, with 1 electron left. Okay, and for carbon, we're going to be C plus and 1 minus. Okay, so this time we are removing electron from a neutral atom. So this time we could use this to compare the energy change and why causing this increasing in energy. Okay, so now again, I want you to describe the general trend and also spot out any highlights on the diagram, any exceptionals on the diagram. Okay, so this periodic table is here to help you to locate the atoms. Okay, so first of all, what is the general trend across a period and also across a group? Okay, down the group. Okay, so first of all, what is the trend for the first ionization energy down the group? Okay, so we could take a look at the noble gases. Okay, so the first one, helium, second one, neon, third one, argon. Okay, what is the trend here? We could also look at group one, okay, hydrogen, okay, normally we don't consider it, and then group two, lithium, sodium, group one, lithium, sodium, and group two, beryllium, and this is magnesium. Okay, what is the general trend for first ionization energy down the group? Hello, anyone?
What?
What is the trend for first ionization energy down the group? Okay, so for example, what's the trend for first ionization energy from helium to argon, or beryllium to magnesium, boron to silicon? Down the group, the
ionization energy is lower down the group.
Yeah, okay, so the ionization energy decreased down the group. Okay, so that's the first trend you need to jot down. Right, and what's the reason for that? Why down the groups first ionization energy decrease? Okay, anyone? Any idea why down the groups the first ionization energy decrease? What's the difference between neon and helium?
Electron shell.
Yep, okay, so it got one more electron shell in neon, so the outermost electron is further away from the nucleus, so it's easy, the attraction is weaker, and it experiences larger shielding effects, so it should be easier to be removed. Okay, so that's a reason for that, so please jot it down. Okay, so okay, that's because the larger the atom, okay, so the easier it is to remove the outermost electron shell. Outermost electron. It is two. Okay, so that's the first general trend you could spot out. And then the next one gonna be, what's the trend across a period? Okay, so that's for period one. okay, hydrogen and helium. And the parts I circle with yellow is just for the second period from lithium to neon. And then for the third period is from sodium to argon. So what's the general trend across a period?
Increase.
Yep. Okay, so the first ionization energy increases generally. Okay, so we see some exceptionals and we're gonna discuss it. Okay, so what's the reason for this increasing trend? Why the first ionization energy generally increases? Okay, so second period, lithium, beryllium, boron, carbon. What's the difference between these two, lithium and beryllium? What's the difference between these two? Anyone?
Between what and what again?
Between lithium and beryllium.
多余了比较长。
Yeah, and at the same time.
Huh?
Okay, so one more electron means they're gonna have one more. Okay, if the number of electrons is different, the number of what should be different as well?
Charge.
Charge, they're all atom. Number of electrons should equal to number of for an atom. Proton. Yes, okay, so you can see beryllium got one more proton in the nucleus. So we say the effective nuclear charge is higher for beryllium because it got more protons in it. So the outermost shell electron gonna experience stronger attraction towards the nucleus. Okay, so that's why if we want to remove an electron from beryllium, we're gonna provide more energy to do that. Okay, so let's write this down. As we go across the period, the proton number increases. I always say the effective nuclear charge they increase. Okay, so for lithium, it got 3 protons in the nucleus, so the effective nuclear charge +3. For beryllium, it got 4 protons in it, so +4. Okay, so the outermost electron receive greater attraction, okay, towards the nucleus. Okay, so that's a general trend. Okay, we say it's generally increased, but also you could spot out 2 exceptionals on this diagram. Can you spot out what element is it? Sorry. Right, so here, okay, generally increase, but there are 2 decreasing parts. Okay, so what's the element here? Okay, so if that's lithium, beryllium, this one going to be boron, and then carbon, nitrogen, oxygen. Okay, so this one, boron, and this one, nitrogen. Okay, so what causing this two decreasing in ionization energy?
그거 oxygen.
Boron. Sorry, this is oxygen. Yep, you're right. Okay, so this is nitrogen. Yep. Okay, so if they are located on the same shell, same distance, and as we increase the number of protons, they should have an increasing trend in first ionization energy. But here we got two decreasing exceptionals. So that means they are not located on the same distance to the nucleus. Okay, so here it tells you that in the same shell, we may have some subshells. Okay, so let's write this down, and later we will be able to explain this. So delete this. Okay, so first there are two exceptions. To the general trend. Okay, so one is boron. The second one is oxygen. Okay, so now without introduce the subshells, we would not be able to explain that. So I'll leave this part later. Okay, later we're going to come back to this. Okay, so the conclusion, but now at least we could draw a conclusion, which is that these 8 electrons in the second shell are not in identical position. Okay, so the 8 electrons in the second shell okay, so this provides evidence of the existence of subshell. Okay, and similarly to the shell that we discussed in grade 9, okay, when they have 8 electrons in it, we say it got fully filled outermost electron shell, so it's more stable. Okay, so it's going to be the same for subshell. Okay, when it's fully filled, it's going to provide extra stability. But this time, okay, even sometimes it's half filled, it can provide extra stability. Okay, so now let's introduce what are the subshell. Okay, so here another new term you need to remember, which is orbital. Okay, sorry. Finish copying this, or you get an idea in your mind. Okay, so here, the new term you need to learn is orbital. So what does orbital mean? You must remember the whole sentence. Okay, so the term orbital is used to define the region where it has a high probability of finding an electron around the nucleus. Okay, so it's describing the region that we could find the electron. Okay, so the orbitals of an atom are arranged according to their energies. So the shells or the energy levels are composed of orbitals. Okay, so when we join different orbitals together, they form shell, okay, or energy levels. Okay, so orbitals are subshell we just talked about. Okay, so here there are two types of orbital you need to learn, and you need to be able to draw the shape of it. Okay, so first is the s orbital. So for s orbital, it got a spherical shape. Okay, so these subshells, these s orbitals, they have the lowest energy level, so it will be filled with electron first. Okay, and for each orbital, it can accommodate 2 electrons. So if we got 3 electrons, we must put 2 in the s orbital first, and then we could start to fill in the p orbital, okay, with the next energy level. Okay, so that's the first orbital, s orbital, spherical shape. Then when s orbital are fully filled with 2 electrons, then we can start to fill in the p orbital. Okay, so for p orbital, they have a dumbbell shape. Okay, and they got slightly higher energy level compared to the s orbital. And for p orbital, okay, again, each of them can accommodate 2 electrons, and there are 3 p orbitals. So in total, they could accommodate 6 electrons. Okay, so for p orbital, we have pz orbital. So you can see the dumbbell shape is along the z-axis. And for py orbital, it's along the y-axis. And for px orbital, it's along the x-axis. And the way that we draw it is usually, okay, if it's okay, what is that pz orbital? So we just draw this shape. Okay, so that's how we draw the 2D diagram to represent the p orbital. Okay, so this one is a pz orbital. So for py orbital, you can either, okay, change how you label the axis, or you could draw your dumbbell along the y-axis like this. Okay, so different way to draw it. But remember, you will be asked to draw the shape of s orbital and pz, py, px orbital. Okay, so total s orbital accommodate 2 electrons. P, Z, Y, X orbitals total hold 6 electrons. Okay, so altogether 8 electrons. That's how we allocate the 8 electron in the second shell. Okay, so let's rethink how we put the electrons in the shell, okay, using those orbitals. So in the first shell, okay, so for example, hydrogen and helium, okay, so they only have s orbital. They are called 1s orbital from period 1, so it's 1s orbital. Okay, so for hydrogen, it should have 1 electron. So if we use an orbital electron configuration, it should be 1s1. Okay, so the 1, this number should be superscript, okay, on the right-hand corner. And then for helium, it got 2 electrons. So remember, we need to fill in the lowest energy level first. Okay, so we should put them, both of electrons, in the 1s orbital. So we say 1s2. This 2 represent there are 2 electrons in the 1s orbital. Okay, so that's for the first shell. Okay, hydrogen, helium only got s orbital. Okay, so only 2 electrons. And then start from the second period. Okay, for all the atoms in the second period, they're going to have s orbital and p orbitals. And remember, we fill in s orbitals first. Okay, so for boron, okay, 2, 3. Okay, so these 2 electrons in the first shell gonna be put into 1s orbital, so 1s2. Okay, and the 3 electrons in the second electron shell, so we're gonna fill in the lowest energy level orbital, which is 2s orbital. So for 2s orbital, it can house 2 electrons. Okay, and then because there are 3 electrons in total in the second shell, so the next one we're gonna put in the 2p orbital. Okay, and here you don't know whether it's put in 2pz, 2py, or 2px, so we just write 2p in general. Okay, and then for oxygen, okay, 2, 6, that's a electron arrangement. So let's see how we could write the electron orbital configuration. So again, 2 electrons in the first shell going to be put into 1s orbital, so 1s2. And then 6 electrons in the second electron shell, so must fill in 2s orbital first, okay, so 2s2. So there are 4 electrons left behind, and then we're going to put them into 2p orbital. So 4 electrons need to be put into 2p orbital, so 2p4. Okay, so that's how we use this to represent the arrangement of electrons. So from period 3, it's gonna get a bit more complicated. They're gonna have not just s orbital and p orbital, but also d orbitals as well. Okay, but the shape of d orbital is not required in IFY syllabus, so I'm not going to show you here. But for d orbitals, it has 3 types of for d orbital, it has 5 types of orbitals, so each of them gonna hold 2 electrons, so total you're gonna hold 10 electrons. So 2 electrons in 3s orbital, and then 6 electrons in 3p orbital, 10 electrons in 3d orbital. So total, the third shell can accommodate 18 electrons. Okay, so this is in 3s orbital, this in 3p orbital, and these in 3d orbital. Okay, so to summarize those terms we have learned, the energy level, the shell, and then the subshell, and then the orbitals refer to this table. Okay, so energy level of the shell is what we talked about in grade 9, using the circle to represent the location of electron. So we got first electron shells, the second electron shell, the third electron shell, fourth electron shell. And for the subshell, we are discussing 1s, 2s orbital, 2p orbital, 3s orbital, 3p orbital, 3d. And then, okay, for 2p, we could then describe it as 2px, 2py, 2pz, and then 3px, 3py, 3pz. And for d orbitals, the shape we're not going to discuss it, so just list it here for your information. Okay, so if you want to learn more, you could go and search online. Okay, so here just pay attention, orbits and orbitals, they got different meanings in chemistry, so be careful when you use them. And the detailed explanation, you could go to watch this video. Okay, so you need to be clear what's energy level, so the shell, and then the subshell, 2s, 2p, 3s, 3p, 3d, okay, and then the orbitals. Okay, so how do we actually put those electrons in those subshells and or in those orbitals? We need to learn some rules to fill them in. Okay, so not just simply 2s first and then 2p, but we need to go into more detail. Okay, so there are 3 rules that you need to learn. Okay, so the first one is the off-ball principle. So in this principle, it states that electrons should fill in the shells or orbitals, subshells or the orbitals with the lowest energy first. Okay, so that's what I just talked about. It must fill in 1s orbital first. So we must put 2 electrons in the 1s orbital, and then we could start to put the 3rd electron in the 2s orbital. Okay, it's not going to be 1 in 1s and then 1 in 2s. Okay, so here, for example, beryllium 4 electron, so it must be 1s2, 2s2, not 1s2, 2p2. Okay, you can see 2p got a higher energy level than 2s, so we must fill in 2s orbital first. Okay, so how do you know the energy level of those subshell? Okay, so you're gonna write the subshell like this: 1s, 2s, 2p, 3s, 3p, 3d, and 4s, 4p, 4d. Okay, so the rest of them you don't need to worry too much about it in your syllabus. But the exceptional is here. Okay, so pay attention. 3p, after 3p, you must fill in 4s before 3d. Okay, so you may put a highlighter to label this part. Okay, so you must fill in 4s before 3d. Okay, 4s got lower energy level compared to 3d. Okay, so we're gonna see some examples. So after you arrange those subshell like this, you're gonna draw arrows, parallel arrows like this. So you're gonna fill in 1s first, and then 2s, and then 2p followed by 3s, and 3p followed by 4s, and then to 3d. Okay, so take a look at the example here. So what is the electron configuration in sp and d notation of magnesium? Okay, so magnesium got 12 protons. The atomic number for magnesium is 12. Okay, so what's the electron arrangement in terms of the shell? Right, so how many electron shell it has for magnesium? Anyone? 3. Okay, 3. So total got 12. So first electron shell hold 2 electron, and then second electron hold 8 electron, and then we're left with 2 more. Okay, so that's the electron arrangement we have learned before. Now we need to use SPD notation. Okay, so we're gonna follow the sequence and fill in those 12 electrons. Okay, so for magnesium, I'm gonna write like this. Okay, so we start with 1s. Okay, so 1s orbital subshell, it can hold 2 electrons. So we'll write like this. And after that, we go to 2s. So 2s orbital, again, 2 electrons for that. And then 2s orbital is fully filled, and then we move on to 2p orbital. Okay, how many electrons can 2p orbital hold? How many I should put for 2p? Anyone? Right, so for p subshell, okay, we got px, py, pz. Okay, each of them can hold 2 electrons. Right, so total pz 2 electron, py 2 electron, pz 2 electrons. So how many?
6.
6. Okay, so we put 6 for that. Okay, so now we've arranged 10 electrons, so just 2 more to deal with. So after 2p, we go to 3s. Okay, so we write 3s2. Okay, so that's a electron configuration for magnesium in SP and D notation. Okay, so now for potassium, can you try to write it? So for potassium, it got atomic number of 19. Okay, so how do you arrange them? Remember, follow this sequence when you fill in the electrons. You try to work it out. Yep. Okay, so sorry. 2881. Yep. So how do you write it in terms of the SP and D notation? Okay, anyone have worked out the answer? You could unmute yourself and let me know, or type in the chat box. Rachel, have you worked out the answer?
Only the first 3 letters.
Yeah. What are they?
1s2.
Yep.
2s2. 2p6.
2p6. Very good. Okay, so you have to deal with these two numbers, 2 and 8. Okay, so let's consider how to put those 8 electrons. Okay, so after 2p, we need to go to 3s orbital. Okay, so let's write 3s first. Okay, so how many electrons can we put in 3s orbital?
2.
2. Okay, so we finish with 2 in this 8 and then left with 6 electrons. After 3s, we go to 3p. Okay, so how many in total we could put in 3p?
6.
6. Okay, and then after that, where should we go? 3d or 4s? Okay, what's the next number and what's the next subshell I should write here? Which way should we go? 4s or 3d? Alright, so remember this arrow shows you the direction. You should go to 4s instead of using 3d. Okay, 4s got lower energy level than 3d. Okay, so the last electron, this outermost electron, we should put in 4s subshell. Okay, only one of it, so it's 4s1. Okay, so that's the electron configuration for potassium. Okay, get it? Okay, so now please try those checkpoint questions. Any questions so far? Okay, so if no, let's complete those checkpoint questions together. Okay, so it's on page 9 of your notes. Finish? Okay, so again, we're gonna take turns to answer the question. So just wait for maybe 1 more minute. Okay, so let's start from part A. Okay, Sumi, can you let us know your answer for part A? What's after 4s?
For P.
Okay, and 2 boxes.
I'm not sure.
Okay, it's okay. So remember, you need to memorize this pattern. So remember this sign. If I put it here, you need to memorize the concept next to it. So remember to put 1s, 2s, so horizontally, the first shell and the second shell and this subshell. Okay, and you always follow this pattern, draw an arrow, and then follow the direction of the arrow. Okay, so here on this table, it go up to 3s, BP, and then 4s. Okay, let's find it on our diagram. So 3s, 3p, 4s, and then we finish with this arrow, so we're going to start again from here. Okay, and follow this, we have 3d and then 4p. Okay, so we can carry on, just follow the direction of this, then after that we should go 5s. Okay, so the correct answer for this one should be 3d and 4p. Okay, so just follow this. So here, let's fill in 3d and 4p. Okay, so this diagram, very important, so later spend some time to memorize it. Okay, so next one, Larissa, can you tell us the answer for part B?
It's used to define a region where it has a high probability of finding an electron around the nucleus.
Yeah, very good. So you just copy the definition on your notes, so memorize that. Okay, so the next part, because it's hard for you to draw, so I'm gonna just show you the answer. So for an s orbital, you just draw a circle. Okay, and then for the p orbital, okay, because it didn't tell you whether it's py or pz or px, so you just draw the dumbbell shape like this. Okay, and then next one, state the total number of electrons occupying all the p orbitals in one atom of chlorine. Okay, so Emily, what's your answer for C?
I don't know how to do.
Okay, let's work it out together. So for chlorine, what's the atomic number? You have a periodic table with you?
17.
17. Okay, so let's try to work out the electron configuration first. So chlorine, 17 electrons. So how to arrange them?
2H7.
2A7. Very good. So now let's turn it into SPD notation. Okay, so how to do that? We begin with 1s. So 1s,
2,
2, and then followed by
2s,
2s. How many?
2,
2. Very good. And then followed by this string. Okay. After 2s, we should have
2p,
2p. Yes. How many in 2p?
6,
6. Very good. Okay. So now we've sorted out 10 electrons in total. Okay. These 10. Now we still have 7 electrons. We need to arrange them. So what's after 2p?
3s,
3s. Okay. How many? 3s.
2,
2. Okay. So now total here 12 electrons. Okay. So 5 left behind. So where should we put those 5 electrons? Okay. So what's after 3s?
3p,
Yep. 3p. So how many electrons in 3p?
5,
5. Okay. So let's double check. 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 5, 17. Okay, match with electron, the total number of electrons in chlorine. Okay, so very good. Now you've got the electron configuration. So what's the total number of electrons occupying all the p orbitals in chlorine? So in chlorine, yep, correct. So in chlorine, it has filled 2p orbital and also 3p orbital. Okay, so in all p orbital, so we need to have 6 plus 5, which give you 11 electrons. Okay, so that's the answer for part C. Very good. Okay, so the next one, state the number of electrons present in an ion of calcium. Who's next? Marcus, please. In calcium, so calcium got atomic number of 20.
Sabat.
Okay, very good. So 20 electrons for calcium atom. Now it's 2 plus, so what's 2 electrons? So it should be 18. Okay, and then the last part, the ionization energy of sodium are shown in the table. So please put a tick when we have removed an electron from s orbital. Okay, so Hayden, can you try this one?
Jesus，最難嗰啲你先揾我，玩嘢。
Take your time. Okay, you're gonna do it stepwise. So you could write out the configuration and then tick the box accordingly.
其實佢問緊啲咩？
It's similar to this one. Okay, just ask you to find the electrons in the s orbital this time, not in the p orbital. Alright, so again, let's begin. So what?
Sodium 嗰個
Okay, so let's work out the electron configuration for sodium together. So sodium atomic number is 11. Okay, so what's the configuration?
281.
Yep, and then in terms of SPD?
1s2. 2s2.
2, and then?
2p6.
Yep, and then?
3s1.
Yep, okay. So now, total you got 11, okay? 11 electrons. And then this one, the first one, which one we are removing among all those 11 electrons? The first ionization energy is removing the electron from where?
3s1.
3s1. Okay, so is it from a s orbital?
Yeah.
Okay, so we put a tick for this.
Oh.
Okay, so can you spot out the rest of them?
What？ 咁之後嗰6個都係 p orbital，所以就隔6個係嘛？
Yep,
Yeah.
very good. So the next one gonna be
8.
8.
Wait.
And then any more?
And then 剔晒啦，係咪嗰啲？
Yep, very good. Okay, so this one is from the 3s orbital, 8th and 9th from 2s orbital, and then 10th and 11th from 1s orbital. Okay, so far so good, right? Just take some time to get familiar with the sequence, okay? And later on you're gonna be it's gonna be really quick. You just follow the sequence and fill in the number. Okay, S orbital always hold 2 electrons, P always hold 6 electrons. Okay, so that's the first rule you need to remember. Fill in the lowest energy level first. Okay, so let's introduce one more rule. Okay, then the Hans rule of maximum multiplicity. Right, so what does this rule state? So it states that electrons should be filled in different orbitals of the same energy as possible. Okay, so we need to put in, remember the subshell for 2p, we got px, we got pz, we got py. Okay, so they are of the same energy level, and we need to try to fill in them separately, and then we start to put the 4th electron in the same, okay, in the same orbital. Okay, so here, this example, if we got 1s2, 2s2, 2p3, okay, for those 3 electrons, we're gonna put one in the px orbital, one in py orbital, and one in pz orbital. Okay, so we try to avoid putting 2 electrons in the same orbital, okay, because electrons carry negative charge. If we put them in the same orbital, they're gonna repel each other. Okay, so we try to avoid that. So here it said pairing up should be avoided as possible as it results in repulsion between electron pairs. Okay, so when possible, we try to separate them. Okay, but of course, if we have four electrons in the p subshell, we have to put one paired with another electron. So we need to start to fill in one of them, for example here, which is to fill in px. Okay, so the sequence we do that is, again, we put one in px, one in py, one in pz, and the last one we start to pair it up. Okay, so it's gonna be 2px. Okay, 2px2. Okay, when we got no choice, then we put them together. Okay, so that's the Hans rule. Okay, still okay. Okay, and then the last one, Pauli exclusion principle. Okay, so that's built upon here. So remember, we have 2px orbital, 2py orbital, 2pz orbital. Okay, and when we have 2px orbital filled in with 2 electrons, how we should arrange these 2 electrons to minimize the repulsion. Okay, so according to the Pauli exclusion principle, so after electrons pair up in an orbital, okay, for the previous example, they paired up in px orbital, okay, they should have opposite spin in order to become more stable. Okay, so first of all, the opposite spin, what's electron spin? I'm not going into detail in this syllabus, but I've attached a website that explains the detail what is actually electron spin. But for simplicity, you just need to think about the electron spin like the pattern or the pathway that the electron travel. So it's gonna have each electron, for example, this one spins up. So that's a pathway for that electron to travel. And then if it spins up, it's gonna generate a net magnetic field. Okay, and then if we got another one that spins down, okay, so it's gonna generate another magnetic field. And because they have opposite direction, so there the magnetic field gonna cancel out. So there's no net magnetic field. Okay, so according to Pauli exclusion principle, when they pair up, they should spin in opposite direction so that there is no net magnetic field generated. Okay, so this box represents an orbital. Okay, so for example, we got s orbital and then 2p, 3 of them. So they represent 2px, 2py, 2pz. Okay, so in each orbital, when we have 2 electrons in there, right, they should have opposite spin. One spins up, one spins down. Okay, to avoid, to minimize the repulsion. Okay, so that's one of the representation. You can see use arrows like this. Sometimes you could also see the arrow join like this. Okay, so both of them are accepted. Okay, so look at an example of sulfur. Sulfur got atomic number of 16. Okay, so when we fill it in, 1 s orbital, 2 electron. Okay, one spins up, one spins down. And then we got 2 in 2 s orbital, 1 spins up, 1 spins down. Okay, and then we got 6 in 2p orbital. Okay, 2 in 2px, 2 in 2py, and another 2 in 2pz. Why so lagging? Sorry, give me a second. I want to restart this. Okay, better. Okay, so carry on. We have worked up to 2p. Okay, so 2, 2, 6, 2p6. And then we go on to 3s orbital, 2 electron in 3s. Again, 1 spins up, 1 spins down. And then finally 6 electrons in 3p. Okay, so remember, according to the Hans rule, we try to separate them. Okay, so the first 3 should be put in one in px, 1 in py, 1 in pz. Okay, and the 4th one, when we start to pair up, we have to put it in the same orbital now, but make sure it got opposite spin to the original one. Okay, so that's one way of representing it. That's a box notation. Okay, and another one is similar to what we have learned in grade 9. So we can use the arrangement of the noble gas from the previous period. For example, sulfur is from period 3. So we could use neon to represent this part. Okay, so 1s2, 2s2, 2p6. So neon actually represents this part. And then we just show the arrangement of electrons in 3s orbital and 3p orbitals. Okay, so this part, this is representing this part. It's equivalent. Okay, so you have to be able to recognize this kind of representation.
Wait, what?
Like sofa, because sofa is from period 3. Okay, so we could use neon, which is the noble gas from period 2, to represent this part. So we don't have to write the box for 1s2, 2s2, and 2p6. Right, so we just show.
你呢啲嘢會 upload 翻嘅係嘛？
What?
你 record 緊㗎嘛係嘛？
Yeah.
之後你擺喺邊度？我要睇翻呢啲課太亂。
You want me to upload it? Because I need to edit before I upload it. I need to cut out. I tried to do it because my iMovie got some problem. I don't know if it can be.
唔使 cut 啦。
Okay. Get back to this. Okay. So for sofa, it's period 3. So we just show the electrons in the outermost shell. Okay. So outermost shell, the third shell, got 3s subshell and 3p subshell. And also for 3p subshell, it got 3 orbitals. Okay, so each box represents 1 orbital, px, py, pz. Okay, so to simplify that, we could use neon. That's the noble gas from the second period to represent this part. And then we just show the arrangement for the outermost electron shell. Okay, let's see one more example. Maybe it will make it clear. Okay, if we got chromium, okay, so it's 24, so it's from period 4. Okay, so this time we could use argon as period 3 noble gas, and then we just show the arrangement of the outermost electron shell. Okay, so we just show D and 3D and 4s orbital. Okay, but here we got one more thing we need to consider. Remember, just now I said when it's fully filled or half filled, it's gonna provide extra stability. Okay, so originally we should fill in 4s orbital first and then 3d orbital. Okay, I'm gonna move to this one. Right, so according to this diagram, we should have 3p fully filled and then 4s fully filled, and then we can move to 3d. Okay, so that's the first rule we've learned. Fill in the lowest energy level first. Okay, 3p, 4s, and then 3d. But because when it's fully filled or half filled, okay, it provides extra stability, and 3D, 4s, they got very similar energy level. Okay, so we try to achieve this extra stability by filling one more electron in 4s. Okay, so we're gonna remove electron from 3D to 4s to achieve that extra stability. Okay, so here. Right. Can I copy this? Copy. Please? Yeah. Never mind. Okay. So after this, yeah. Okay, so we're gonna remove one of the 3D to 4s to achieve that. Okay, so we're gonna get 4s with sorry. We're gonna remove one of the electrons from s to d. Okay, we got 5 orbitals in d. 5 orbitals in d. Okay, so we now have each of them. All right, that's for 3D. now 5 electrons, so they all have 1 in it. So it's half filled. So it provides extra stability. And now we also got 1 in 4s. That's again is half filled. So that provides extra stability. Alright?
啲 orbital 係擺幾多粒㗎
Total 10.
？OK，
Because for 3D subshell, it got 5 orbitals. So each of them can hold 2. So total 10 electrons.
OK，
Alright? So this is preferred. So although 4s orbital got lower energy level, okay, we don't fill it in with 2 electrons. Okay, so we move 1 to 3D to make it half fused and achieve the extra stability. Okay, so that's one of the special case you need to remember. And another one is copper. So you can highlight these 2 elements. Okay, you will only be asked to write the electron configuration up to 36. So that's the 2 exceptions you need to remember. Okay, so for copper, okay, total 29 electron. So according to the rule that you have learned, we fill in 4s first, and then 3D. Okay, so in principle, okay, we should arrange them as 4s2, 3D 9. All right, so we got S, 4s fully filled, and then move on to 3D. But again, because 3D and 4s, they got similar energy level, and we want to achieve half fuse. Okay, so this time we're gonna have 3D and then 4s. Again, we're gonna move one of the electron from 3s and put them into 3D. So it's being up, down, up, down, up, down, up, down. Okay, so now we got 10 electrons in 3D. So it's fully filled for 3D orbital. So that's gonna provide us with extra stability. And there's only 1 electron for 4s. Okay, so that's a little bit different to the rule stated. So that's the exception you need to remember. Okay. Any question up to here? Okay, I think we've covered a lot today. So next week, we're gonna try to apply these rules in some questions and see whether you really understand them or not. Okay, anything you want to ask before I end the lesson?
你幾時 upload 啦
Weekend, give me some time.
我 send 條 link 過嚟。
Yep.
OK，唔該。
Any other question?
琴日你有冇 record？
Yep.
Thank you。upload 埋嗰條啊。
Okay.
我唔明個 checkpoint 啊。
Which one? Which page?
9
Which question? Which part?
C 同埋 F。
C. Okay. So, do you understand the electron configuration in terms of SPD? This part.
Yes.
Okay. So the question asks you state the total number of electrons occupying all the p orbitals. Okay, p orbital doesn't say whether it's 2p, 3p, 4p.
得啦，我明啦，我明。但係 F 我真係唔明。
Okay, so F, I believe you are okay up to this one. Okay, so you know the configuration, how you work this out. But for ionization energy, you're gonna look at it backwards because we're gonna remove the outermost electron first. Okay, so we're gonna remove this one first. from the third shell, right? So the outermost electron, this one is in 4s subshell. Okay, so that's an electron removed from an s orbital. It's from 3s, so we take the first box. Okay, the second one, this one, we're removing one from 2p. Okay, and then we remove the third one from 2p.
我得啦得啦，我明
We
啦
remove from the highest
我
energy
全部
level,
都明
so
啦，
we
我而
get
家全部
backwards.
都明。
Okay, and yes, what's the question, Larissa?
For the neon one on page 11.
Yeah. Okay. Yeah.
I don't know why you have to add 3s and 3p because isn't neon like 10 electrons?
Yep. But this part as a whole, we are trying to represent the electron configuration for sulfur. Okay, so the yellow part, yeah, this parts represent the arrangement for neon, but the whole is to represent sulfur. Okay, sulfur got 16 electrons in total. Okay, so on top of the arrangement, the same as neon, we still got 6 more to deal with.
Okay, I understand.
Yeah. Anything else?
我们找到了。
Okay, I'll see you
Thank
next
you. Bye
week.
bye.
Bye. Bye. Have a nice weekend. Bye.
Bye。星期四
Bye.
今日。
Yeah.